Formal proofs for relational logic are analogous to formal proofs for propositional logic. The main difference is that there are additional mechanisms for dealing with quantified sentences. In the Fitch system for relational logic, we include all 10 of the rules of inference for propositional logic. We have negation introduction and negation elimination, implication introduction and implication elimination, equivalence introduction and elimination, and we have introduction and elimination rules for conjunctions and disjunctions. In addition to these rules of inference for logical operators, we have 4 new rules for quantified sentences. Introduction and elimination rules for both universal and existential sentences. Let's look at them in turn. If you're like me, the prospect of going through a discussion of 4 rules of inference one after another sounds a little repetitive and boring. However, it's not really so bad. Each of the rules has its own quirks and idiosyncrasies, its own personality, if you will. In fact, a couple of the rules suffer from distinct excess of personality, if you ask me. If we are to use the rules correctly, however, we need to understand these idiosyncrasies. Universal introduction allows us to reason from arbitrary sentences to universally quantified versions of those sentences, subject to a constraint that we'll discuss shortly. Typically, UI is used on sentences with free variables to make the quantification explicit. For example, if we have the sentence hates Jane X, then we can infer for all X hates Jane X. Note that we can also apply the rule to sentences that don't contain the variable that is quantified in the conclusion. For example, from the sentence hates of Jane Jill, we can infer for all X hates of Jane Jill. Also, from the sentence hates of Jane Y, we can infer for all X hates of Jane Y. Admittedly, these are not particularly sensible conclusions. However, the results are correct, and the deduction of such results is necessary to ensure that our proof system is complete. There's one important restriction on the use of universal introduction. If the variable being quantified appears in the sentence being quantified, it must not appear in any active assumption. And by that I mean an assumption in the current subproof or any superproof of that subproof. For example, if there is a subproof with assumption P of X, and from that we've managed to derive Q of X, then we cannot just write down for all X Q of X because P of X appears in an assumption in that subproof. If we want to quantify a sentence in this situation, we must first use implication introduction to discharge the assumption, and then we can apply UI. In the example here, we first apply implication introduction to derive the conclusion P of X implies Q of X, and that's in the parent of the subproof containing the assumption. And then we apply universal introduction to derive for all X, P of X implies Q of X. Okay, that's that. All right, I'm just going to keep rolling here. Hopefully you can cut and splice and chop and whatever else you do to make this work. Over to domain closure. Let's see, where are we here? Okay. Yeah, okay. Finally, for languages with finite Hebron bases, we have the domain closure rule, or sometimes written DC. For a language with object constants sigma 1 through sigma n, the rule is written as shown here. If we believe a schema is true for every instance, then we can infer a universally quantified version of that schema. Suppose, for example, we have a language with just 4 object constants, A, B, C, and D. Then we could write an instance of the domain closure rule, as shown here. If the sentence, in this case an implication, is true of A, and is true of B, and is true of C, and is true of D, then it's true of everything, and so we capture that with a universally quantified statement. For all X, P of X implies Q of X. Now, you might wonder why we restrict DC to languages with finitely many ground terms. Why not use it for languages with infinitely many ground terms as well? It'd be good if we could, but this would require rules of infinite length, and it would be impossible to generate finite proofs with such rules. Fortunately, we can get the effect of such sentences through the use of induction, which is discussed in a later lesson. Universal elimination, our second rule, sometimes called UE, allows us to reason from general to the particular. It states that whenever we believe a universally quantified sentence, we can infer a version of the scope of that sentence in which the universally quantified variable is replaced by an appropriate term. We'll explain this condition of what makes a term appropriate in a moment. But first, some examples. Consider the sentence, "For all x hates Jane x." From this premise, we can infer that Jane hates Jill, that is, hates Jane Jill. We can infer that Jane hates her mother. We can even infer that Jane hates herself. In addition, we can use universal elimination to create conclusions with free variables. For example, we can infer hates Jane x or hates Jane y. In using universal elimination, we have to be careful, however, to avoid conflicts with other variables and quantifiers in the quantified sentence. This is the reason for the constraint on the replacement term. Consider the sentence shown here. For all x, there exists a y hates xy. That is, everybody hates somebody. From this sentence, it makes sense to infer there exists a y such that hates Jane y. That is, Jane hates somebody. However, we do not want to infer there exists a y such that hates yy. That is, there's somebody who hates herself. The problem here is that the quantifier in the sentence has captured the variable being substituted. Let's formalize this. An occurrence of a variable nu in a sentence phi captures a term tau if and only if tau contains another variable mu, and the occurrence of the first variable nu lies in the scope of a quantifier of mu. What? That's a fairly complicated definition, I think. Fortunately, it's easy to understand with an example. Suppose we want to substitute mother of x for y, and there exists an x hates xy. We cannot, because the occurrence of y in there exists x hates xy captures mother of x. Why? Because mother of x contains a variable x, and the occurrence of y lies in the scope of a quantifier of x. So all we need to do is to avoid this problem. In what follows, we say that a term is substitutable for a variable nu in phi if and only if no free occurrence of nu captures tau. Some texts say that tau is free for nu in phi. For example, mother of Jane is free for y and hates of Jane y, since the term contains no variables at all. The term mother of x contains variables, but it's free for y and hates Jane y, since there are no quantifiers to capture the variable. The term mother of x is free for y and there exists hates zy, because it does not contain a variable that is quantified. On the other hand, the term mother of x is not free for y and there exists x hates xy, because there is an occurrence of y in the sentence that lies within the scope of a variable in mother of x. Finally, and this one may be a little tricky, for some of you at any rate, mother of x is free for y in this complex sentence. Although there's a quantifier of x in the sentence, it's okay, because the only free occurrence of y, the only one in which we're going to do the substitution, lies outside the scope of this quantifier. Okay, avoiding conflicts of this sort is the main reason for the substitutability condition in our definition of universal elimination. When using this rule, if we obey the law, we won't get ourselves into trouble. Our next rule, existential introduction, EI, is easy. Not much personality here. If we believe a sentence involving a term tau, then we can infer an existentially quantified sentence in which one, some, or all of the occurrences of tau have been replaced by the existentially quantified variable. For example, from the sentence hates Jill Jill, we can infer that there is someone who hates herself. There exists an x hates xx. We can also infer that there is someone Jill hates. That is, there exists an x hates Jill x. And there is someone who hates Jill. There exists an x hates x Jill. And by two applications of existential introduction, we can infer that someone hates someone. That is, there exists an x, there exists a y such that hates xy. Note that in existential introduction, it's important to avoid variables that appear in the sentence being quantified. Without this restriction, we can get ourselves into trouble, but if we avoid such variables, we won't have any trouble whatsoever. Finally, we have existential elimination, or EI. Suppose we have an existentially quantified sentence with scope phi. And suppose we have a universally quantified implication in which the antecedent is the same as the scope of our existentially quantified sentence. And suppose that the conclusion of that implication does not contain any occurrences of the quantified variable. Then we can use existential elimination to infer that consequent. For example, if we have the sentence, there exists X such that hates Jane X, and we have the sentence, for all X, Jane hates X implies that Jane is not nice, then through one application of existential elimination, we can conclude not nice Jane. This exercise tests your understanding of our rules for quantifiers.